Okay, so I definitely got cut off at the end of the last screencast, but you got the gist of it. Answer was 5, and I was going through all the walks of length 3. Now, that was a brief overview on adjacency matrices. What other kind of matrices are we going to talk about today? Transition matrices. Remember those? Related to eigenvalues, eigenvectors, Markov chains, going from the probability of going from a future state, from a current state to a future state, represented in with transition diagrams, transition state diagrams, or transition matrix, from which we can find a long-term steady state matrix. So, a couple of things. Now, a transition matrix, I'm going to let you read this. Let me pause here and I'm going to let you read this first. Now, a couple of things here. We're seeing a little bit more vocab. The probability of moving from one vertex, I'm reading right here, of moving from one vertex to any of the adjacent vertices is defined to be the reciprocal of the degree of the vertex in an undirected graph. Remember, the degree of the vertex is how many edges go to that vertex, right? So how many direct connections between another vertex. And for a directed graph, it's going to be the reciprocal of the out degree, all right? So how many arrows are going out from it. Now, this is where we combine what we learned earlier about transition matrices. That the probability of moving from one vertex to another is going to correspond with an entry in a transition matrix. Now, remember, transition matrices look like this, where we go from the current state to the future state. So we're reading from column to row, all right? Whereas in the adjacency matrices, we read from the row to the column. Sorry, I know, it's annoying. Let's talk about a little bit more. Now, steady state probabilities, you remember those things, right? They indicate the proportion of time that would be spent at each vertex if a random walk was undertaken for a long period. So the transition time between the vertices is ignored. Now, steady state probabilities, remember, is when we raise a matrix, a transition matrix, to a sufficiently large power that the probabilities do not change. The values in the matrix do not change. Guess what? That's kind of how Google's algorithm started out. And by the way, Google was founded by a UMD grad. Sergey Brin was a University of Maryland College Park grad, undergraduate studies, degrees in computer science and mathematics. So if you're thinking of studying math, I strongly encourage you to, even if it's just a minor, just do it. You might get some genius ideas if you don't already have them now. All right, so let's talk about some problems. All right, so here's our problem. In this graph, vertices A to F represent web pages, whoop whoop, and the edges indicate links between the pages. Remember, edges don't have to be straight edges, they could be curved. For example, page A has links from both C and F and contains links to B, D, and F. Let's construct the transition matrix for a random walk around this graph. Okay, so remember, first of all, a transition matrix is not an adjacency matrix, all right? A transition matrix is showing the probabilities of going from one vertex to another. So let's remember what we defined as those probabilities on the earlier slides. Let me back up 2 slides here. Now, this graph that we're dealing with in this example is a directed graph. In a directed graph, the probability of moving from one vertex to any of the adjacent vertices is going to be the reciprocal of the out degree. Okay, so let's keep that in mind, and let's start constructing our matrix. All right, so problem A. Do I have enough space here? Yeah, let me do that right here. Okay, so A through F, and remember, current state are the columns. So A, B, C, D, E, and F, and then again A, B, C, D, E, and F. La 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 la. All right, now out degree. The out degree for vertex A. All right, let's count this out degree. How many out arrows come from vertex A? 1, 2, 3. And they're going to vertices F, D, and B. So if the out degree is 3, the reciprocal of that is 1 over 3 for F, D, and B. All right, so from A, remember this is our current state, going to the future state, back to the future. Then we're going to have 1 over 3 from A to B, from A to D, and from A to F. Don't have any. We can't get directly from A to C, or A to E. So I'm going to put zeros here. All right. Let's look at vertex B. Let me erase what we did here. All right. What is the out degree for vertex B, and where does it go? How many out arrows come from B? Just 1. And it only goes to vertex D. So from B to D, reciprocal of 1 is 1, zeros everywhere else. All right, from C, what is the out degree? Again, you could probably, if you get it, pause or fast forward this recording and just check your work. I'm still going to walk through it though. From C, what is my out degree? I see 1, 2. All right, so 1/2 from C to A, and 1/2 from C to B. Everything else is a 0. Out degree for D. I see 1, 2, 3 again, so 1 out of 3, 1/3 rather, to B, C, and F. 1/3, 1/3, and 1/3. Zeros elsewhere. From E, I see 1 arrow going out from E. I'm not going to write that. And it's going to D, so from E to D, right here. Zeros everywhere else. And from F, 1, 2. All right, so going to A and to E. So 1/2 is the reciprocal of 2. 1/2, and zeros elsewhere. Aha! Okay, this is our transition matrix. And now let's find the steady state probabilities for this network. All right, so let's just call this M. All right, that's our matrix right there. And let's put that into the calculator. I'm not going to show you how I put that into the calculator. I'm just going to do that with my handheld calculator. And let's raise it to powers sufficiently large so that each of the entries in our matrix is no longer changing. So raise it to a big power, then raise it to the next power and see if it's changed or not. That'll tell you if you found the steady state probabilities. I'm going to pause here and do that, and I hope you do too. And then let's check, see if we got the same number. Okay, so when I raised it, this matrix to the 50th power and then to the 51st power, I got, remember, a steady state matrix not just has repeating values from one power to the next, but it also has repeating values across columns for every row. All right, so for A, B, C, D, and E, we're going to have just these 6 numbers, 0.130. And that's going to repeat all the way across that first column. That first row. 0.207, 0.109, 0.326. Oops, sorry, there's F, right? E and F. 0.206. I meant 0.326. 0.076, oops, and 0.152. Now, these are our steady state probabilities. So therefore, what does this mean? So I just said this is raised to the 50th power. What do these numbers mean? It means that there's a 13% chance of ending up at point A or site A, since these vertices represent web pages. 20.7% of landing on site B, almost 11% landing on site C, so on and so forth. So rank the vertices in order of importance, meaning which website are you most likely to land on? Which website are you most likely to land on versus which ones are you least likely to land on? Just look at these numbers. So D has the highest probability, then B, then A, oops, sorry, then F, then A. That is an F. Oh, baby, F, A. Then C, then E. And that's how to make a transition matrix and interpret a transition matrix. All right, so what I'm going to have you do now is, this thing, I'm sorry about that, guys. I want you to try this problem on your own. I'll pause here, I'll do the workout, and then I'll bring us back and explain what I did so that you can check your work and then proceed to practice. Okay. It was taking a bit of a long time to do the system of equations, but look, we can see that we're getting similar answers with the solving by using a system of equations and simply raising this matrix from the undirected graph in part A to a sufficiently large power. I'm going to tell you I raise it to the 50th power and then I raise it to the 51st power, and it did not give me the same numbers. So I tried a different large number, raised it to the 100th power and then the 101st power, and I got these values right here. All right, so that was my steady state. And as we can see from my start in solving this system of equations, we know that A is going to equal C and B is going to equal D. I didn't end up getting those exact values, and I'm about to get kicked out of the building right now, so I needed to stop here. And we see that A and C equal each other, B and D equal each other. All right, and remember the probabilities for an undirected graph, all right, from, meaning current state, to any of the other vertices is the reciprocal of the degree of that vertex, all right? So A has 2, is a degree of 2, so the reciprocal of that is 1 over 2, and those values are assigned to B and D, and that is right here and right here. Remember, for a directed graph, we're going to look at the out direction. All right, so we're going to take the reciprocal of the out direction from that vertex. All right, so that's a wrap on this. I believe on Thursday, actually, half of our class is going to be taken up with a presentation or a discussion with Youth for Equity. So I think on Thursday, we're just going to be looking at calculus review if anyone has a need for that. Your homework, which you already saw in your assignment, is going to be to do these selected problems from these 3 exercises, of which we already started. All right, guys, I will see you on Thursday. Bye-bye.